Welcome to lecture number 2 of CIVE 360. And let's start by reviewing what we talked about last time, the essence of this class, and that is if we take some solid and we load it, we have some sort of resultant force. I'm just going to write it like that for right now. Then we have a couple of things that we're interested in, namely is the question, will it fail? And the second question that we want to answer is, how much does it move? So those two questions are really behind most of what we're doing in this class. And then we have this kind of variable hierarchy. We say that the solid has this load applied, and as we load it, the solid deforms. So we can go out in our backyard and get some little aspen sapling sticking up like that, and we push on it, and it bends. It goes like this. So we're going to quantify that by using the symbol U, which means the displacement. That displacement then, and it's different, that displacement is, it's different depending on where we are in the solid, but that is linked to a measure that we're going to introduce known as the strain. Then that strain has a relationship with a quantity that is known as stress. That's actually what we started last time. And then that stress is related to a resultant force which balances the applied load. So if we had to write out the essence of this class in a small little mnemonic device, it would look something like this. And what we did last time then is we started with just a blob of a solid, sorry about that, and we took it and identified some point P. We surrounded it by an element of area. I guess I should put that up here. That is our element of area that we just called delta A. And we have some resultant force that acts over that area that we called delta F, that's a vector. And then we can break that down into two components, one that goes tangent and one that goes normal. So the one that is normal to the surface we call delta N. I'm not going to repeat everything that we did last time. The one that is parallel to the surface we call delta V. And we introduced two measures. The first was sigma, and that is what is known as the normal stress. It has the dimensions of force per length squared. Remember, force is an honorary dimension. It's not one of the basic 7. And we get that by shrinking down the area. So we take the limit then as delta A goes to 0, and we take the magnitude of that small component of force delta N. I guess it doesn't really have to be small, but the normal component, and then we divide it by the delta A. So it is a limiting process to get it to be a pointwise measure, and that's known as sigma, which is the normal stress. We also then do the same thing with tau, which is the shear stress. That also has the dimensions of force per length squared. And so again, the dimensions are the generic ones, so force length squared. When we say units, that would be pounds per square inch or newtons per square meter. And the shear stress then, same thing. We take that little area and we shrink it down. Delta A goes to 0, so we go down to a point of the magnitude of delta V divided by delta A. So there's this limiting process, and what I want to highlight here is that these are pointwise measures. By pointwise, that means that they exist at one discrete point in space. So for complicated structures, let's say we have an automotive component that we're working at Ford, and we're analyzing the stress inside of a component during a crash, then at every single point inside that solid, the stress could potentially vary, and we want to figure out what that's going to be. But for now, we're starting with this relatively simple system, and we're just identifying the the normal stress, and then the shear stress. What we want to do now is immediately start to apply an example. So we're going to do one for both of these. So an example that we're going to use, and this is going to calm you down, I think, a little bit, because when I was an undergraduate student, anytime I looked and I thought, oh gosh, I have to take a limit, there's some sort of mathematical operation, that's going to be quite involved. But what tends to happen, especially at the start of class, is that it turns out that we don't have to take that limit. In other words, we're going to use an example that is known as the uniform stress. And what that means is, and in fact I should say examples, because we're going to do one of each. The uniform stress basically means that the stress over our cut area doesn't change. So the stress over the cut area is basically uniform or constant. And so we don't have to take the limit. So I'll write it like this. We have to do the limit, and the answer is no. We don't for certain types of solids that are pretty simple in their appearance and in their loading. So we get away with it. So even though we're introducing it as a limiting concept, and we want to remember that, and we want to use that, there are many, many times when we do not have to do that. So let's take a look at these examples. And the first one that we'll do is an example of a uniform normal stress. And we're going to pick a really simple problem. Let's say that we have a cross-sectional area that is 2 inches by 1 inch, rectangular, and it goes something like this. So we can imagine something that might look like this that we can pick out of the rack at Home Depot. And we just pull on it. So I'm going to pull with 100 pounds this way, and 100 pounds this way. And we would like then to make a cut perpendicular to the applied load direction. So our cut is going to be perpendicular to the 100 pounds. So the cut would look like this. I would slice it like that. In fact, it looks a lot like the cross section. So that's going to be our cutting plane. And when I do that, then, what we find is that the resultant force goes exactly backwards. If I draw it to the side, it would look like this. There's my cut. It's going like this. So what I've just drawn is these two arrows, like so is this. So that's the length that I've got. So I've got 100 pounds this way. So again, this arrow is this arrow. I'm just viewing it from the side. So what happens is then there has to be something on that back face that's going to balance that. So I'm going to draw a dashed arrow like this. And that has to be 100 pounds as a resultant because it has to be in static equilibrium. So in this case, we can see basically that the entire delta F that we've got is all going into the normal force. It's going into the delta N. And that is going to be the entire 100 pounds. So there is, we have 100 pounds total. So it stays all perpendicular to the face. There is no delta V. So let's write that up. There is no delta V for this particular cut. So what that means is that we can say sigma, instead of writing out the limit, we just have to write the total force divided by the total area. And that makes things much, much simpler. So we can say 100 pounds divided by the 2 by the 1 inch squared. And so we get then that sigma is equal to 50 psi. So we would say then that the normal stress is uniform over that particular cross section, and its value is 50 psi. What this also allows us to do then is introduce a sign convention that we're going to be using for this class. And that sign convention goes like this. So we'll say the signs of sigma. And it's fairly simple and it's very intuitive. If it is in tension, in other words, there is a pull on our face, it's going to be positive. If there's a compression on our face, in other words, a push, that is going to be negative. So the sign convention for the stresses, it's very intuitive, it's kind of natural. So if I pull something out, I'm making it grow longer, it's going to be considered to be a positive normal stress. If I'm pushing it, it would be negative. So what we would do up here is we would denote the sign by using the letter T for tension. So we could say T or we could say positive. Those would be synonymous. So we would say plus or T. So those are the symbols that we're going to use. Now my preference is for you to use T and then in compression. So that would be T. If it's in compression, then we'll typically write C. In my opinion, that is the way to go because it reminds you of what your signs are going to be. If it's going to be tensile or compressive, then you can get used to writing T or C. All right, so that's a very simple problem, but it's one that's kind of useful to us. Now, what's happening then, if we took a small segment, let me draw another view of that back face, like so. So now the right face where we originally had the 100 pounds, that's going to be going this way. So in other words, this cut is still this one, but now I'm reorienting it. So I'm looking at this back face over here. So the phrase I like to use for the normal stress is linked to the fact that along this location, there's all of these values of the tiny bit of force divided by that area. So anywhere we go over that cut face, there's the same value of sigma. So that is the sigma, and that is 50 psi, and that's going to be in tension. So that would be a visual picture. At every point, we've got an arrow. So there is an arrow of sigma is equal to 50 psi at every point on that cut face. And so because of that reason, I like to use this phrasing. I like to think of stress as being a field of arrows. So it is a field of arrows. It's like you've got, you're an archery competition or something, and you've got all these arrows on that face. They're everywhere on that particular cutting plane, and they all have that orientation. So they're all going in the direction of those little arrows that I've got right here. And at every single location, they're a value of 50 psi. So we have one arrow that shows the force, and then we've got a field of arrows then that shows the point-wise transfer of what's happening inside of that solid when we make that particular cut. All right, so that's our first example for the normal stress. We've got now PSI, those are the units, and now we know something about the sign convention for the normal stress. And that's a great spot to stop part A of our lecture.